Hi, my name is Gili Lifshitz, and I'm going to present here comparison and linking between LDPM and FDEM modeling for fracturing in concrete. The co-authors that we work together are Eunice, Penkfei, Vahid, Carl, Giovanni, Nalon, and Sanjay. The outlines for today are introduction, LDPM theory, LDPM geometrical characterization of concrete mesostructure, FDEM theory, FDEM and LDPM 3D simulation for calibrating the parameters, and conclusions. Pipeline concrete weight coating consists from few layers such as CWC, that stands for concrete weight coating. Then underneath this layer there is a reinforcement layer that can be from different types of reinforcements. Underneath that, ACC, that stands for anti-corrosion coating, and the last is line pipe. The main function of it is to provide bottom stability to submarine pipelines. It is also commonly used as a method for mechanical protection of the pipeline against impact. The main design issue for pipeline CWC is to ensure that the effect of various loads presented during the installation and the operation will not damage and cause movement of CWC, such as tension, bending, and other environmental loads. The main bending considerations occur during installation. S-curve as lowered from both stinger to seabed. In operation, the pipeline is subjected to temperature, bending, accidental loads, drop objects. While designing the pipeline CWC, they need to take into account that it won't get damaged or movements. Damage in CWC leads to loss of concrete, pipeline instability, reduction of mechanical protection. The tension and bending moment can cause movement in CWC that cause buckle mitigation solutions, may damage field of joints. Stiff concrete may cause high stress strain concentration. Recently, there are special concrete mix designs such as well-packed aggregate size distribution, such as concrete with additional superplasticizers, like concrete with large amount of voids, like concrete with wired reinforcement or other reinforcement like fibers. The compressive strength and the Young modulus defined in the standards are not suitable for these unconventional concrete mix designs. And using the Young modulus and the compressive strength as the only parameters are not enough. We want to define the full stress strain curve to predict the behavior. Therefore, in the recent years, multi-scale analysis methods were developed to predict the concrete behavior based on the components. In our work, we simulated CWC under a different combination of loads that represent the mechanism caused to it. In addition, we examined two types of multi-scale methods, and we are working on linking between them. LDPM stands for Lattice Discrete Particle Model, and it simulates the mesoscale concrete behavior. LDPM calculates the displacement between the aggregates, where there are three directions of displacement. There is tensional between the aggregates and two other shear directions. From the displacements, the stress and strains are calculated. And for the fracture behavior, it is calculated from the constitutive law, which have three subcategories: The first is the fracturing and cohesive behavior under tension and tension to shear. The second is the poor collapse and material compaction under high compressive strength. And the third is the frictional behavior. The LDPM first generates the mesostructure. It takes into an empty container and inserts inside particles from the largest to the smallest. And it checks that the volume of the aggregates does not overlap with other volume components such as sand, water, and others. The size distribution is calculated from the Fourier curve. Voronoi-like mesh is built on top of Delaunay tessellation of the particle locations. Here, a 2D dimensional model is shown. In the left, where black lines show the interface boundary, where one element is aggregate bonded with mortar, and the black line represent the interface between them. The interface are called facets. In the right, facets are shown for 3D model that act as interface element. In LDPM, failure can occur only at interfaces. So the different element sizes is associated with the heterogeneity of the material. Here we can see aggregate with the package. The package is the mortar, and the failure propagates between these packages in a very complicated directions. Another method we examined is FDEM. FDEM stands for Finite Discrete Element Method. FDEM is an explicit method that can simulate from the meso to the macroscopic scales in 2D and 3D. Interaction and forces transfer between the elements are governed by penalty values, which cause stress and deformation in tetrahedra that can cause yielding and failure in cohesive crack elements. The crack propagates under mode 1, which is tensional, mode 2, which is shear, and mode 3, which is a combination between mode 1 and mode 2. Yielding and separation in the elements control the nonlinear reaction. Adoption of the same mesh topology for both models would be the best, as such an approach would allow fracture to propagate along the same faces. We are still working on solutions to achieve this goal. The complications are related to different mesh quality requirements for each model. For right now, we simulated both the models for UCS test, which stands for uniaxial compressive strength, and for BD, which is the Brazilian disc test, indirect tensional test. And this, we can see here the setup for FDEM model for both of the simulations type. We examine finer meshes for both of the types of simulations. So this is the results of the different simulation types. For the FDEM, the crack elements may yield and crack and break under mode 1, 2, and 3, depending on the local stress. For the LDPM, as explained above, the initial mesh is subdivided into clusters of elements. Crack may form between clusters when a local measure of damage exceeds a local allowable. And also we can here see the experiment results of XRF analysis, we see here that the crack pattern of the LDPM and FDEM fits really good with the experiment results. Here we can see the experiment results and the crack pattern of LDPM under BD simulation type and for FDEM model. We see that we get a really good fit of results between the crack pattern of the experiment and the simulations, which is very important for accurate modeling. So the numerical simulations of LDPM and FDEM were calibrated by comparing the stress-strain curve with the experiment results. We see that we get a very good fit of results for both of the models. The black curve represents the experiment results. The blue curve represents FDEM simulation. The orange curve represents finer mesh simulation, that we can see that the sensitivity of the mesh is independent. Also, we can see the red curve and the green curve that represent LDPM simulation, where the red curve represents finer mesh. Here also, we get independency for the sensitivity of the mesh. So we also calibrated the FDEM model with the Brazilian test. And the LDPM, it's kind of a validation process by using the same parameters with different experiment type. But you can call it also for FDEM a validation process. So the red dots represent the LDPM and the green dot represent FDEM simulation, and the blue dots represent the experiment results. If you see, there is a large scatter of results. However, the average of the results fit really good with the numerical simulations of both of the models. Here we can see the calibrated parameters for each model with the experiment results, calibrated with the experiment results. And both of the models were successfully calibrated and validated at this point. And for the conclusion, LDPM and FDEM were successfully calibrated and validated. Modeling of concrete material under different combination of loads predicts a realistic stress-strain relationship, which is really useful for designing CWC. Modeling of shear and transfer between the CWC and ACC are very important and can be simulated with these models. Load conditions and material models, CWC, can be simulated with these models. Also, we can investigate parametric studies to investigate the sensitivity of the CWC, and then we can predict a key consideration for designers. Okay, thank you very much. Hope your stresses are a little bit released from the corona, and see you later. Bye-bye.